Welcome. This is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York. And this is Exploration. Every week in Exploration, we discuss the fascinating world of science and its impact on society. And today, leading off, we're going to summarize some of the top stories in science and also answer some of the emails that I get. First of all, we are rapidly approaching the 50th anniversary of the historic moon landing. It's hard to believe that, yes, it was 50 years ago that humans first set foot on our nearest celestial neighbor. I remember that incident very well because, well, I was in the Army at that point. The Vietnam War was at its height. Hundreds of GIs were dying every week, and I was in the military, about to be perhaps stationed in Vietnam. And in our military base, we had a television set, and there it was. We saw live footage of the landing of the Apollo 11 spacecraft on the moon. But personally, I had mixed feelings about the whole thing, because on one hand, it was a tremendous milestone for humanity, but for us, in basic training, about to be shipped out to Vietnam, it was a totally different perspective. We had to realize that we were confronting the most basic issue of all, and that is life and death. Are you willing to die for your country for a cause that, well, perhaps you're not quite sure about? Well, these are some of the thoughts that raced in my mind when I saw humans walk on the surface of the earth. But let's summarize what's happening in outer space now. First of all, SpaceX has been making headlines repeatedly. This time, Elon Musk's company sent 60, not one, not two, 60 small satellites into a successful orbit around the planet Earth with the eventual goal of sending hundreds of mini satellites to create a truly planetary internet system. A system that would service poor areas of the world, areas that are quite difficult to reach by standard microwave devices. And so we're talking about a truly planetary internet. And we should also point out that some of the rockets used by the SpaceX launch were used not just once, not just twice, but 3 times. And so we're entering the era of reusable spacecraft. This means that costs are going to drop. In fact, Elon Musk of SpaceX has said that costs could drop by a factor of perhaps 10. Think about that. It costs $10,000 to put a pound of anything into orbit around the planet Earth. What would happen if that were to fall down to $1,000 per pound? And perhaps even less than that. That would change the whole dynamics of exploring outer space. Not just that, of course, but the moon as well. Jeff Bezos, richest man in the world, recently announced that his Blue Origin project, his Blue Origin spacecraft program, is definitely shooting its sight to the moon. In fact, he wants to set up an Amazon-type delivery system whereby products would be shipped from the Earth to the moon. He has big dreams, among them to create the Earth as a park, as a garden in outer space, with all heavy polluting industries put into orbit around the planet Earth. Also, talking about outer space, here's an embarrassing statement. We used to think that we knew the age of the universe. Textbooks say that the universe is 13.8 billion years old. Now we have a new result that's throwing that whole figure into doubt. The universe could actually be perhaps 1 billion years younger than previously thought. This is embarrassing because all the textbooks may have to be revised, and it means that, well, something is missing in our understanding of the expanding universe. Well, first of all, how do we measure the age of the universe anyway? I mean, no one was there to witness the Big Bang 13.8 or so billion years ago. So how do we do it? Well, first of all, we use something called the Doppler shift. If I have a yellow star and it moves away from you, this means that light, the yellow light from that star, is stretched. Therefore, the light becomes slightly reddish. If a yellow star moves toward you, light coming to your eyeball is slightly compressed. and so it becomes slightly bluish. So a redshift signals an expanding universe. A blue shift signals a contracting universe. When we look in the heavens at distant galaxies, bingo, we find it right there, a red shift taking place as the universe begins to expand. Then we know the rate of recession of the galaxies, and then we just simply run the videotape backwards. And bingo, that gives us the age of the universe. Simply by running the videotape backwards on an expanding universe, we can now calculate the age of the universe at 13.8 billion years. However, there are other ways of doing it too. There's the Planck satellite, a European satellite in outer space right now, measuring the microwave radiation emitted from the infant universe. In some sense, we're looking at baby pictures of the infant universe. In fact, it looks like an explosion. In fact, it is. It is the Big Bang itself. Now, when you take those numbers and you compare them with the numbers we see today with nearby galaxies, we find a mismatch. And that's quite embarrassing. It doesn't mean that Einstein was wrong. No, it means that we have to put a fudge factor into our equations. This fudge factor is called dark energy. It is a term found in Einstein's equations. It is the energy of nothing, the energy of the vacuum. Even vacuum, even the state of emptiness has a little bit of energy associated with it, pushing the galaxies apart. And so we now have to revise our textbooks. Perhaps there is more dark energy out there than we previously thought. So our textbooks may be wrong. First of all, our textbooks say that the universe is basically made out of atoms. We know that's wrong. The universe is basically made, first of all, out of dark energy. Perhaps 73% of the matter energy content of the universe is dark energy pushing the galaxies apart. Dark matter, which keeps the galaxy together, that makes up about 23% of the universe. Hydrogen and helium, which make up the stars, they make up perhaps 4% of the universe. So what about us? What about you and me? What about oxygen and carbon? Well, the higher elements, i.e. us, we make up perhaps 0.03% of the universe. In other words, we are the oddballs. Most of the universe is dark. Most of the universe is dark energy, dark matter, and hydrogen and helium, and we are the oddballs. We only make up 0.03% of the entire universe. Well, speaking about the universe, let's talk about life in outer space, specifically the search for the holy grail of planetary astronomy, to find a twin of the Earth in outer space. That is the holy grail. So far, our satellites, like the Kepler, have discovered about 4,000 exoplanets orbiting other star systems. But let's be fair about this. 96% of these exoplanets are much larger than the planet Earth. In fact, they're the size of Neptune or the size of Jupiter. Huge gas giants in outer space. But now, reanalyzing the data from Kepler, we found out that we made a slight calibration mistake. And we now realize that the search for this doppelganger, the search for a twin of the Earth in outer space, could be closer at hand than we previously thought. First of all, by reanalyzing the data, scientists found that they miscalibrated the way they calculate small planets, planets the size of the Earth. Now, first of all, we locate these planets because they eclipse the mother star. When these planets move in front of the mother star, light is diminished. In fact, if a Jupiter-sized planet were to move in front of the mother star, light drops by about 1%. So you can imagine that an Earth-sized planet would drop the sunlight by a tiny fraction of 1%. But that fraction of 1% is visible with telescopes. Now we realize that we miscalibrated that. You see, stars are not uniform. The rim of the disk of a star is slightly darker than the interior of a star. So when a planet eclipses the mother star by moving in front of it, the eclipse is irregular. It's not perfectly uniform. And that non-uniformity was not taken into account. When we do that, we found that 60 previously unknown planets are actually Earth-sized. In fact, one of them is even smaller than the planet Earth. This is amazing because we once thought that the Earth was one of the smallest objects we could detect with our instruments. No, one planet is 60% the size of the planet Earth. Now, don't get your hopes up about finding aliens in outer space because most of these planets are still rather inhospitable. They are very close to the mother star. Temperatures are way above 100 degrees, and so it's quite hot on some of these planets. But one of the planets in this new calibration came out to be the size of the Earth, or roughly the size of the Earth, and moderately temperate temperatures were found. In other words, perhaps we are finally zeroing in on a doppelganger in outer space, a twin of the Earth. Then once we find the twin, we have to make sure that there's oxygen and water vapor in the atmosphere of that planet. Once we find that, that would be a prime candidate for the search for extraterrestrial intelligence in outer space. Again, we're not there yet. Out of 4,000 planets, we simply found just a few that are Earth-like, and we have yet to analyze their atmospheres to see whether they have enough water vapor and oxygen to support life as we know it. We're not there yet. Also, if you're a fan of HBO, perhaps you watch more than just the Game of Thrones. Perhaps you also watch the series about Chernobyl. And so the question often comes up when people watch that series, and that is, was Chernobyl really the world's greatest nuclear accident? What about Fukushima? And for that matter, what about secret military accidents that took place in the former Soviet Union that perhaps were even worse than Chernobyl? So in other words, the question comes up, how bad was Chernobyl when we compare it with 3 Mile Island, Fukushima, and the Kushtin incident that happened back in the 1950s? Well, to a physicist, the first thing you ask when you look at a nuclear accident is, what was the fission product inventory that escaped? In other words, what fraction of the core escaped into people's backyard? That is the key number which allows you to then estimate how dangerous this accident was. Well, we know what happened at Chernobyl. At Chernobyl, they were making repairs in the control rod system, and they partially disengaged the control rods. Now, that's potentially dangerous because that's like disengaging the brakes of your car. It means that your car cannot stop anymore because the brakes have been disengaged. Well, you do have to make repairs on reactors, of course. And so the workers there disengaged partially the control rod system. But then the unexpected happened. There was a transient, a sudden burst of energy in the core. Now, these transients, well, they happen, and these transients are due to the fact that there are irregularities, imperfections, blah, 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 inside the core. But usually the control rods catch it in time. Well, this time the control rods were disengaged, and it's sort of like driving a car where the brakes are disengaged, and all of a sudden there's a spurt. There's a spurt of energy in your car, and your brakes don't work anymore. That's what happened at Chernobyl. It turns out the transient was much worse than expected, and it became autocatalytic. It basically fed on itself and created a huge explosion which blew the roof right off the reactor. Not only that, but hydrogen gas. Hydrogen gas was also created by all the radiation that was involved. Radiation takes water, splits water apart into hydrogen, and that hydrogen gas is explosive. And so the combination of a runaway transient plus a hydrogen gas explosion blew the top off Chernobyl, causing perhaps 30% of the core to be released into people's backyards. That is incredible. 30% of the core of a nuclear power plant being flung into outer space. Now let's compare that to what happened at Fukushima. At Fukushima, we didn't have a transient. We had a 9.0 earthquake, a gigantic earthquake, one of the largest ever recorded in the history of science. This was no ordinary earthquake. This was a monster of an earthquake which created a tidal wave, this huge tidal wave which hit the Fukushima reactor, catching the workers off guard. Now, to be fair, the Fukushima reactor was built to withstand earthquakes. Let's be fair about this. But a 9.0, that's off scale. I mean, think about that. 9.0, one of the largest earthquakes ever recorded in the history of science, happened right off the coast of Japan, creating a gigantic tsunami which overwhelmed the emergency core cooling system at Fukushima. Did they insert the control rods? Yes. They hit the brakes of the reactor? Yes. But they were overwhelmed by this gigantic tidal wave of water which went right over all the protective layers that they had built, and it caused 3 reactors, not 1, not 2, but 3 reactors to melt. In fact, to melt down completely. In fact, when you look at the devastation, you realize that all 3 had hydrogen gas explosions. All 3 released radiation sufficient to break up water into H2O, and the H detonated and blew the top off 3 reactors. Now, fortunately, and this is the saving grace, fortunately at Fukushima, the core remained basically intact. Melted, totally disintegrated and melted, but the core inventory did not escape into the environment except for small amounts of, let's say, iodine-131, strontium-90, and cesium-137. And so we did not have the situation like in Chernobyl, where a good fraction of the entire core was sent into the air. At Fukushima, there was a hydrogen gas explosion. Radiation did escape. But at Fukushima, we did not have a good fraction of the core inventory being sent into the air. Then, of course, you have to look at the human tragedy. Radiation from Chernobyl was picked up sailing over Europe. In fact, it eventually sailed over New York City. I remember being in New York watching the radiation count in milk. And sure enough, you could see a small spike in the radiation being picked up in milk right here in New York City because the cloud circled the entire planet Earth. And so we have this huge accident that took place, and it was much worse in Chernobyl than it was at Fukushima. However, the agony is going to go on for decades. What did they do at Fukushima? First of all, they sent in firemen. Many of these firemen received lethal doses of radiation. They're heartbreaking pictures of these workers suffering enormous radiation damage, dying like flies in the hospital. What finally stopped this raging accident at Chernobyl? The Red Air Force. That's right. The Red Air Force were called in. They put shielding on the bottom of their helicopters, and they dumped borated water, huge amounts of borated water on this raging accident at Chernobyl, and then they sandbagged it. That's right. They encased it in a tomb of concrete. They sandbagged the entire thing, stopping the accident from taking place, but the core is still melting away. Believe it or not. And you can prove this because it rains. It rains in Kiev, and the rain seeps into the core. Water is a moderator. It helps to slow down the neutrons, and radiation levels rise. You can actually see that with a Geiger counter. Every time it rains in the Chernobyl area, Geiger counter radiation levels rise, and it means that the accident is still in place. What are they going to do at Chernobyl? Eventually, they may have to put a sheet underneath Chernobyl's core to prevent it from sinking into the groundwater. But at Fukushima, it's much worse. Much worse. First of all, we have 3 melted cores, and only recently have robots been able to, like submarines, take pictures of the melted core at these reactors. That's how bad it was. 3 melted cores, and only recently have robots that have been reinforced because of the enormous radiation there. Only recently have robots been able to swim in the reactor core water and get pictures of the core. This makes it possible for the first time in years to actually begin the process of extracting some of this melted uranium from the core at Fukushima. Then the next question is, what about the health effects? Well, iodine-131 is a very dangerous radioactive chemical found in nuclear meltdowns. Half-life of iodine-131 is about 8 days, so in a few weeks' time, most of the radiation is gone. But iodine concentrates in the thyroid gland of children. And that's one of the first things you see after a nuclear accident. You see levels of iodine-131 in the thyroid glands of, let's say, children, which increases their susceptibility to thyroid cancer. In about 5 years' time, leukemia starts to form. We know this because we've analyzed the victims at Hiroshima and Nagasaki. And so after about 5 years' time, then you have to worry about leukemia. And then after that, 10, 20 years after the accident or the bombing, you have to worry about solid tumors that begin to form. So it's a never-ending agony. The agony of thyroid cancer, then leukemia, and finally solid tumors that emerge after a nuclear accident. And we know this because we've studied the aftermath of Fukushima and Chernobyl. But then there's something that the press misses, and that is it misses weapons accidents. Chernobyl and Fukushima were commercial accidents, but the granddaddy, perhaps the biggest of all nuclear accidents, and we're not sure because it's largely classified, is what happened in Kushtin in the Ural Mountains, perhaps in the 1950s. Back then, the Cold War was in full swing. Both in the United States and in the Soviet Union, safety controls were lax because there was a race against time to see which country could master nuclear technology, and safety was simply not on the radar screen of many of the directors of these laboratories. Well, near Kushtin, there was a plutonium waste dump. And you have to be careful because radiation is so intense there that it causes bubbles to form. The liquid begins to boil, and that's what happened at one of the canisters containing plutonium waste. The vat began to boil. Hydrogen gas was created, they think, and the hydrogen gas ignited, blowing the top off the vats containing weapons-grade nuclear waste. Aerosolized plutonium then was shot into the atmosphere. What happened after that? Well, we don't know, because a lot of this has been classified. However, there is a book written by Professor Medvedev, Nuclear Disaster in the Urals, which tried to piece together what happened. Now, the CIA got wind of this because all of a sudden in the Soviet publications, strange scientific articles began to be published. These articles talked about the dispersion of plutonium aerosols in the environment. Now think about that for a moment. Why would any sane government in their right mind deliberately release plutonium aerosols into the environment to trace the dispersion of this deadly radioactive material, some of the most deadly radioactive materials found on the planet Earth, in a peaceful environment like a lake? Why would you do this? Well, the CIA began to put two and two together, and they began to realize, oh my God, there must have been an accidental release of massive amounts of plutonium aerosolized waste somewhere in Russia. Well, the CIA then began to look at the map, then began to try to locate where this accident took place, and sure enough, strange things were happening there. All of a sudden, certain villages like Kazli disappeared from the map. That's right, villages simply disappeared. In other words, something big really happened. Now, Dr. Roy Medvedev has tried to reconstruct the size of the cloud, the size of the accident, and of course, much of the details are classified, but it was huge. And it was not iodine-131, strontium-90, or cesium-137 like you found at Chernobyl and Fukushima. No, this was plutonium, weapons-grade plutonium, plutonium used in the manufacture of atomic and hydrogen bombs. And so what really happened there? How many people were affected? We don't really know. A lot of that is unfortunately still classified, but some people think that was the mother of all nuclear accidents. Not just commercial, but weapons accidents as well. Now, to be fair, we should also point out that similar accidents might have happened in the United States, but didn't. The counterpart of this waste dump in the Soviet Union is Hanford, Washington, where we have this gigantic nuclear facility where leaks are the standard form of accidents that have taken place there. Leak after leak after leak. I mean, you look at the roll call of all the leaks and accidents that took place there, and it is astounding. In one incident, for example, workers were looking at a vat of plutonium waste, and they looked inside, and they found out it was empty. That's right, it leaked. The entire contents of the vat leaked into the environment, but they didn't monitor it continually, and so they were shocked to find when they did monitor this one vat that the entire contents of the vat were missing. Well, we could go on and on. The point is that during the height of the Cold War, the two superpowers simply looked the other way and did not look at safety concerns. They did not look at what was really happening right under their noses in these nuclear laboratories. Good day.